So, hello there. We are back with our discussion on the current mirror. So, this time we have brought to you the new circuit referred as Wilson current mirror. So, as you can see in this circuit diagram, this is the diagram of Wilson current mirror. So, this circuit was designed and implemented by Wilson, who was a scientist who was working for the electronics company, and he invented this concept. So our task today is to analyze this circuit and understand how it helps us in improving the performance of current mirror circuit. So there are two words that we use. One is current reference and another word is current source. So essentially, when you design a current source, you want the output current I delivered to the load, and it should be constant. The current should be constant irrespective of the variations in the load. That is the definition of ideal current source. And that's why we need a reference current from which we make a copy of another current, and that current can be used as a current source. Now, the first point that you want to understand, this Wilson current mirror is designed to provide more constant current source or sink. Now, if you recall from our previous discussion, we had these current mirror circuit, something like this, where we took the resistor R and it was our supply voltage, which and we call it this transistor Q1, and collector and the base of this transistor was shorted together, and then another transistor. So because of this resistor, it provided us the input current I in, or let's say I reference. And because of the way this transistor is connected, it produced a voltage, junction voltage, emitter base junction voltage of VBE. So it acted as a current to voltage converter, current to voltage converter. All right, and then we use this voltage source, which is VBE, to bias another transistor actually, and we call it this transistor Q2, and that's it. And we had this collector current of the transistor, which we called it as I out, and we said I out was approximately equal to I in. But more formal analysis gave us the answer that I out was equal to I in minus 2IB, because we see here the I in got split into the collector current of the transistor Q1, and then it got split into IB1 and IB2. So these are IB1 and this was IB2. All right. So if you write I in was IC plus IB1 plus IB2. So assuming the two transistors are equal, their collector currents are equal, and we said that I out, which is the collector current of transistor 2, that is Q2, is equal to the collector current of transistor Q1. Finally, we got this expression, right? So yeah, so here IC, instead of IC, if we take the IC, it would be I in minus 2IB, okay? And the collector currents of the transistor Q1 and Q2 are equal, so IC1 is equal to IC2. So that was our theory. So precisely when we talk about this equation, we don't really have I out equal to I in. Rather, it is somewhat lesser than the I in, and that is because of the base current of this. So this concept was called as static error, or error in the current mirror performance due to the base current of the transistors. To circumvent this problem, there is this arrangement now, which is called as Wilson current mirror. And we are going to analyze this circuit. So there are some set of equations here to help you understand the performance of, and after that we will see how this circuit is connected with proper arrangement, where you use the value of resistor and connect it to supply to draw the input current IR1, and then the output of the transistor Q3, which is shown floating here, is then connected to the load so that the current can be delivered to the load. Now, what you see here, coming back to our focus, taking back our focus to this circuit, we have this input current I in that is coming into the circuit. This is an input side of the circuit again, and this is an output side of the circuit. But if you see this arrangement, Q1 and Q2, as compared to this circuit, here the Q1 is diode connected and Q2 is normal. In this arrangement, the Wilson current, we have just swapped the positions of Q1 and Q2. So Q1 is normal and Q2 is diode connected. So that's how we make this arrangement to build the Wilson current mode. So it will provide us much more accurate input to output current gain. So I in got here, then it is splitted between two parts, IB3, which is the base current of transistor Q3, and then you have IC1, which is the collector current of transistor Q1. And then you see that the transistor Q3 is biased or in such a way that it acts as a voltage buffer, or we can also call it as a common collector configuration. So in common collector configuration, CC mode of the transistor, we know that the voltage at the emitter is the voltage at the base minus the base emitter junction drop of the transistor. So that's how we know from the common emitter. So we say that the emitter voltage follows the base voltage approximately, but it will always be less than one drop of the base emitter junction less than the voltage at the base. And the advantage of using the transistor in a common collector CC mode is that although it doesn't have a voltage gain, it has a voltage gain less than or equal to 1. However, we have the current gain. So current gain of the transistor can be used actually. And there is a sort of negative feedback also from the emitter of the transistor Q3 back to the base of IB1, and therefore we can get this collector current into the branch of Q1, that is then again helps us to control the base current of Q3, and eventually IC3, which is the output current transistor, will be I out, and will in a moment show that I out is equal to I in. Okay, and we'll see that it is approximately more closely matching to the input current. So let me get rid of the drawing. So coming back here, I in gets splitted into two parts right here. And then you have assuming that the Q1 and Q2 are exactly matched. They are the transistor of same types. It means their beta are matched and they have equal base emitter voltages, and they have equal properties. So there is a perfect symmetric condition, and therefore the current IC1 and IC2 can be said to be equal. Therefore also current IB1 and IB2 said to be equal. And then we know that the IC3 of these IE3, which is the emitter current of the transistor, is equal to you can say that IC2 plus 2IB. Okay, so just we are applying the KCL here, IC2 plus 2IB. Okay, now what happens here is that when you apply an input current source into the circuit, you let it flow, the voltage at this node starts to rise. And if this voltage, which is the base voltage of transistor Q3, is sufficiently large so that it exceeds the base emitter junction of voltage of the transistor Q3, the voltage at the emitter of the transistor Q3 starts to rise. Then that makes the voltage of the base of the transistor Q1 and Q2 starts to rise, which gives rise to the base currents, and therefore your collector current of the transistor is started to be drawn. So there is a current flow through the collector of the transistor. So as I said, IC1 and IC2 are equal, and IB1 and IB2 are equal. This is our assumption by which we saying transistor Q1 and Q2 are exactly matched. And we can say that the value of the base current, therefore we can also say that the transistor Q3, base current of the transistor Q3 is also equal to the base current of transistor 1 and transistor 2. So that is our first equation. So we say that base current in the circuit of the transistors is equal to IB1, that is equal to IB2, and it's approximately equal to IB3. Then based on the transistor matching, we said that collector current of the transistor Q1, IC1, is the input current I in minus the base current of the transistor Q3. Simply we are applying KCL at this node. You see IC1 is equal to I in minus IB. So we have the final expression of collector current, emitter current actually I3, that is equal to I in plus IB. Okay, so there was IB term which was hiding in the point, so I in plus IB. And now we get this final expression by saying that I out, which is nothing but the collector current IC3. So we know that IC is equal to IE minus IB, basic transistor equations, and the value of IE, we have it I in plus IB, and it will be minus IB, and therefore IC, which is nothing but I out, is equal to, these terms get cancelled, is equal to I in. So this is an approximation of this expression that we have here. So you see the static error on the first order is removed. But if we do a more thorough analysis of this circuit, then we should get an expression about the transistor current gain, as I can write here with this equation right here. So I will say the difference between the two currents, that is input current and output current, is still there, and which can be finally written as 2 times in divided by beta. So if the beta is very, very large, let's say approximately 200 to 500, it can go. So this difference can be reduced to a negligible level. And therefore our approximately equation will always be this, as you can see right here. Now we have done some analysis about how the Wilson current mirror works. It has advantage about more accurate input to output current gain, and it has an advantage about higher output impedance. The penalty that we need to maintain the circuit as a proper current mirror circuit is the compliance voltages that is dropped between the transistor Q3 and Q2, right? Now, when you actually connect the input current into the circuit, so this current is coming when you make such arrangement of the circuit. What you have is you have a voltage supply Then you use the value of a resistor to set the current IR1 flowing into the circuit, and rest of the circuits are same, except on the Q3 collector pin, you connect the load with respect to VCC, and therefore you basically is also drawing the current through the load right here. Okay. So the current IR1 value can be set as by applying the KVL in this loop right here. So we can write here V plus the value of IR1 is to be calculated. So it will be V plus IR1 equal to uh, V plus minus VBE, that is the voltage drop across of the second transistor, that is this VBE, that is VBE2, and then there is this VBE3 also. This is VBE3. So you basically are coming from like this, and it's going till the ground, common terminal like this, not this one. Okay, so it is VB2 minus VBE3 divided by the value of resistor R. So that's how you get the value of the current IR1. Okay. So another advantage at it is working as a proper current source, and it will maintain its output current constant irrespective of the variation in the impedance of the load. But if there is a supply change or the value of the resistance change, then IR1 is likely to change. Even the supply change or the value of resistor change can happen due to the temperature change. Therefore, the value of input current IR1 is going to change. It will reflect in the output current change. So output current will also no longer be constant. Okay. So you, as a designer, you need to design a current reference or a current source independent of supply, that is the voltage, okay, independent of the temperature and independent of the process. So PVT, that's called as process voltage and temperature. So hope you found this video useful. Stay tuned for more informative contents like this. Till then, explore yourself and like and comment on the video section. Let me know your thoughts, and we will incorporate more entertaining and engaging videos like this to keep you updated with the latest trends in the microelectronic circuit design. Wish you happy learning.